Good afternoon, everyone. Welcome to our presentation on the Deliverance Data Engineering project, where we showcased our skills and knowledge in Python, SQL, database modeling, AWS, operational practices, and agile methodologies. This project involved building a reliable and resilient data pipeline to extract, transform, and load data from an operational database into a data lake and data warehouse hosted on AWS.
These are the members of the Deliverance team. Although we all worked on different aspects of the project at different times, all of us had particular expertise and specialisms which we brought to the group. As was our documentation and automation specialist, getting our CI/CD up and running, and also creating the automated documentation. Billy was our Terraform specialist, helping to deploy our infrastructure smoothly. Oliver and Prub worked primarily on the Python code and developed our extensive testing suite. I concentrated on the overall application structure and linking all the different elements together. This diagram depicts the architecture of our data pipeline. The step function manages the whole process, invoking each Lambda function in turn and passing the output of one to the input of the next. The payload passed is a small JSON object containing information about the tables that are running through the pipeline and the S3 keys to the required objects. All sensitive information and credentials are stored on the AWS Secrets Manager. A CloudWatch dashboard deployed by Terraform for each environment shows the performance of the Lambdas at a glance. A robust, serverless architecture leveraging the power of AWS services.
Our primary objective was to build a reliable data pipeline. We achieved this through an extract, transform, and load process. For data ingestion, we used a Python application running on AWS Lambda. This application ingests data from the TOTSys Postgres database and stores it in an S3 ingestion bucket in JSON lines format. Next, for data processing, another Lambda function remodels the data into a predefined schema using pandas data frames. The process data is then stored in Parquet format in an S3 process bucket. Finally, for data loading, a third Lambda function loads the process data into our data warehouse. To ensure comprehensive monitoring and alerting, we implemented logging using AWS CloudWatch. This setup allows us to track progress, detect failures, and trigger email notifications. We automated the entire process of deployment using Terraform. Additionally, our CI/CD pipeline is managed with GitHub Actions, ensuring smooth transitions across development, testing, and production environments. For data visualization, we used a Tableau dashboard, which provides clear and insightful views of our data. Overall, our structured approach guarantees that the pipeline is efficient, scalable, and maintainable.
One of the largest challenges was designing the architecture of the entire pipeline at the outset. We broke down each individual Lambda into individual utility functions and specified the signatures of these, their inputs, outputs, and any errors, by writing draft doc strings before coding. This identified problems early and led to the decision to use a step function. Another issue was the AWS Lambda layer size limit. We optimized our code and dependencies, and we removed the pandas test suite to fit under the 50 megabyte limit. Using JSON posed challenges with data types like datetime and not a number. We had to handle conversions when importing the JSON data. Some of the tables relied on others for lookups before processing into the star schema, so we had to carefully plan the payload format and the operation sequence to maintain referential integrity. Detailed planning and specification writing ensured clear understanding of requirements across the team and served as a reference when we were writing the code. We often came together as a whole team to brainstorm and troubleshoot particularly sticky problems, and it's this collaboration, along with our varied skills and expertise, that allowed us to overcome these issues and deliver the full product within 3 weeks.
Step functions were chosen for their robust orchestration capabilities, enabling efficient data flow and error handling within our system. At the core of our process lies data ingestion from the TOTSys database, facilitated by the ingestion Lambda. Here, payloads are crafted and processed, referencing objects created and put into the S3 ingestion bucket. Step functions checks for new data to process at a choice state, If no new data is present, subsequent lambdas are bypassed, optimizing resource usage and avoiding unnecessary work. However, when new data is detected, step functions guides the payload to the processing lambda. Following processing, step functions passes the payload to the loading lambda. Concluding our workflow, step functions evaluate the outcome based on the payload status code, concluding on success or transitioning into a fail state. Using Terraform, we automated the deployment of our entire infrastructure. In our project, we organised our Terraform configurations in a directory containing all the necessary files to provision AWS resources as per our ETL diagram. By defining our infrastructure as code, we ensured consistency across different environments. We deployed our resources seamlessly across development, test, and production environments, maintaining uniformity and reducing the risk of manual errors. Our CI/CD pipeline with GitHub Actions facilitated these deployments, ensuring that every change was automatically tested and deployed. Additionally, we implemented carefully limited permissions to enhance security. Each resource was granted the minimal permissions required to perform its function, adhering to the principle of least privilege. In conclusion, using Terraform for automated deployment and maintaining a structured directory for configurations enabled us to manage our infrastructure effectively and securely.
We embraced agile principles and fostered a collaborative environment throughout the project. Using GitHub projects, we meticulously tracked our issues and tasks, making it easier to integrate with our version control. Daily stand-ups kept us aligned and focused, allowing quick resolution of blockers and adapting to any changes. Rotating the Scrum Master role and pair programming promoted knowledge sharing and diverse perspective. This collaborative approach enabled us to keep everyone up to date with multiple parts of the code base, ensuring higher productivity and quality. We used MKDocs with Google Docstrings to auto-generate comprehensive documentation, making our code easier for future developers to understand. The documentation can be found on GitHub's pages. We enforced code quality in our local machines with Git hooks and making sure that work is secure and formatted correctly before pushing code. GitHub Actions then automated tests and checks on every push before merging the main branch. The protection rules on the main branch required code reviews and approvals, ensuring higher quality integration. Our CI/CD pipeline deployed tests on feature branches and production infrastructure using Terraform after merges. This automation ensured seamless, reliable deployments, easy experimentation, reducing errors, and speeding up our delivery cycle.
In conclusion, our Deliverance data engineering project demonstrates our ability to design, implement, and automate a robust data pipeline using modern technologies and best practices. We successfully integrated various AWS services such as Lambda, S3, Step Functions, and CloudWatch to create a scalable and reliable solution. Through this project, we gained invaluable experience in Python programming, SQL database modeling, AWS infrastructure management, operational practices, and agile methodologies. These skills will undoubtedly propel us forward in our careers as data engineers or software developers. Thank you for your attention. We would be happy to answer any questions that you may have.